Welcome to our lesson on 3-dimension geometry. In this chapter, we will be discussing equation of line and plane in space. To begin with, let us refresh the 3-dimension coordinate system. Although as we progress down, you will realize that all the concepts will be discussed in dual language. We will be extensively using vectors which you have just finished as the previous chapter. At the same time, the same concepts will also be learned in Cartesian geometry. So, it is essential to refresh and review what you must have learned as 3-dimension coordinate system in your previous class. To begin with, let us just first look at the 2-dimension Cartesian system, where we have two number lines mutually perpendicular to each other, intersecting at a point which is referred to as origin. In 2-dimension coordinate system, we have set of lines, horizontal line known as the x axis and the vertical line known as the y axis, perpendicular to each other, intersecting at a point which is referred to as the origin. Between these two lines, we constitute what is called as the xy plane. These two lines divide the xy plane into quadrants which are numbered as 1, 2, 3 and 4 as we move anti-clockwise. And you are pretty confident of how the direction and the signs of coordinates in this system are defined. For 3-dimension coordinate system, we take 3 lines which are mutually perpendicular to each other, the x axis, the y and the third axis that we look at is the z axis, which gives the height to a line, a point and the dimension added on. Now, how we define and how we use the orientation of these 3 axes is governed by what is called as the right hand orientation. So, we are looking at a system that is being followed as a right hand orientation, which is defined as you can see here. If you curl the fingers of your right hand inwards and hold up the index finger out, middle finger towards yourself, then the thumb follows the direction of the z axis. So, curl your fingers of the right hand in, hold up the thumb, point out the index finger and the middle towards yourself. Then we take the x axis, y axis and z axis in this direction. That is the convention that we will be following as and when we talk about a 3-dimension coordinate system. Now, these 3 axes taken in space divide the entire space into octants. Octants word comes from oct, 8. So, there are 8 regions that the space is divided into. And what are we looking at most of the times? Our reference would be for the first octant. So, here as you can see, the first octant is defined by the positive x, y and z axis. If you are struggling with visualizing the first octant, then think of the room where you are sitting in and look at the bottom corner of the room. The 3 axes x, y and z will be running along the 3 edges, where z will be along the height of the room. The wall which is in front of you will be the yz plane. The wall on your left is the xz plane and the floor will always be the xy plane. And that is how we are looking at the orientation of our first octant. Correspondingly, there will be 3 more rooms as you see in this picture and 4 rooms below this if you understand and accept this system to be, say, a 2-story building. So, there are 8 pockets, 8 rooms, all sharing a corner which is known as the origin. Now, these octants are definitely going to play a role, but most of the time our work will be in the first quadrant as a point of reference. So, our discussion and our work when we draw on paper or on the board would always be for 3 axes which are the positive x, y and z axis. The other 3 axes can get extended beyond these points. Now, if we are interested in finding the coordinate of a point in space, then how do I decide the position of a point in space? In this case, let us take a point P, which right now looks like lying on a certain plane, but just visualize. So, it is a very, very important thing to start sharpening your spatial and visualization skills here. So, suppose I have a P point which is hanging in space, and from there I drop a perpendicular on the floor which is the xy plane. From that foot of perpendicular, let us draw perpendiculars on the x and y axis. Then the distance measured along x axis from origin where this perpendicular hits the x axis gives us the x coordinate of the point. Similarly, the distance we are looking at measured from origin along y axis gives us the y coordinate, and the z coordinate is the distance again measured along the z axis, which would be same as the height of the point, as in this case marked by the yellow dashed line. That gives us z coordinate. These 3 quantities put together constitutes the ordered triplet. So, in 2 dimension we call the point as ordered pair, here it is defined as an ordered triplet. So, this is how you would be looking at coordinates of a point in space. At the same time, the 8 octants are defined by different axes. It could be positive x, positive y and a negative z axis. Correspondingly, the signs of the coordinates are defined in each octant. This figure illustrates just that. So, in the first quadrant, of course, in the first octant as we have seen earlier, all the 3, that is x, y and z coordinates are positive, whereas in the second octant we have negative x axis, positive y and positive z axis defining the space, and therefore, the coordinates will be negative, positive and positive. Third octant again negative x and negative y, but positive z axis, and therefore, negative, negative, positive and so on. So, if I take a point negative 2, negative 3, negative 6, where would it lie? 7th octant. And if I have a point 4, negative 3, 5, then it will lie in the 4th octant. So, this is how the orientation of a point in space is considered. Now, at the same time as we progress further, you need to recall certain results that you had done earlier as in 2-dimension geometry as well, which played an important role like the distance and the section formula. These results are very easily extended in 3-dimension as well, where a third component in z direction gets added on. The results more or less look very, very familiar. Let us just brush them up. So, here we have 2 points A and B in space, then the distance between these 2 points is given by the distance formula, which just gets extended with z2 minus z1 whole square. At the same time, if I take a point P, dividing the segment AB internally in the ratio m is to n, then the section formula gives me the coordinates of the point P as mx2 plus nx1 by m plus n, my2 plus ny1 by m plus n, and the z coordinate as mz2 plus nz1 by m plus n. So, this is the same 2 results applicable in 3-dimension as well. So, what else we are going to talk about? Direction cosines of a line, a very important concept as we get ready to talk about equation of a line. If I take a directed line L which is making an angle alpha with x axis, beta with y axis and say gamma with z axis, then we define cos alpha, cos beta and cos gamma as the direction cosines of the line. Now, remember that line can be extended on two sides. So, if I extend the line downward, then it will make angle pi minus alpha, pi minus beta and pi minus gamma with the three axes. Therefore, there will be another set of direction cosine. So, every line actually has two sets of direction cosines, but to define the direction cosines uniquely, we take the line as a directed line. Now, let us also look at some of the small results which will also be significant. The notation that we have for cos alpha, cos beta, cos gamma is LMN. They have a relation L square plus M square plus N square equal to 1, and any three numbers which are proportional to the direction cosines are called direction ratios. Some people also call them as direction numbers of the line. Direction cosines of a line passing through 2 points is given by x2 minus x1 divided by the magnitude of the vector joining P and Q, that is distance PQ as well. Similarly, y2 minus y1 upon PQ, z2 minus z1 upon PQ. Now, these results will come in handy. I think now you are ready to try your hand at a very simple exercise. The question says that find the direction cosines of x, y and z axis. Now, we know very well that x axis makes 0 degree, 90 degree and 90 degree angle respectively with the three axes, and therefore, the direction cosines of x axis will be cos of 0 degree, cos of 90 degree and cos of 90 degree. That is 1, 0 and 0 are the direction cosines of x axis. Similarly, you can talk about the direction cosines of y axis which are 0, 1 and 0 and z axis 0, 0 and 1. Now, these quantities will play an important role in our future discussion. So, do keep this little result in mind. One quick question again for you. Find direction cosines of a line which makes equal angles with the coordinate axis. So, we do not know the angle which the line make with the three axes, but that angle is equal. So, would that not make the direction cosines also equal? And so, we have our result ready. If I take theta to be the angle with x, y and z axis, then direction cosines of the line are same. So, L equal to M equal to N, and we know that L square plus M square plus N square is 1. So, that gives me 3L square equal to 1. I get the value of L as plus minus 1 by root 3. Since we do not know the direction of the line, we will accept both the values to be the required. Therefore, direction cosines of line equally inclined to the axis are plus minus 1 by root 3, plus minus 1 by root 3 and plus minus 1 by root 3. So, with this you are ready to start off with more on 3-dimension geometry. See you in our next lesson. Thank you.